Hey everybody, welcome back to another video about calculus. In this video, we're going to be talking about the product and quotient rules, which are essentially our ways of dealing with how derivatives play with multiplication and division. We've talked about addition, subtraction, scalar multiplication, everything like that. Now it's time for products and quotients of functions. So, our first theorem is exactly what it says on the tin. It is going to be the products rule. Okay, so the derivative of two functions, f and g multiplied together, dx of f of x times g of x, is going to be equal to f of x times g prime of x plus g of x times f prime of x. So, first times the derivative of the second plus the second times the derivative of the first. And I know you're thinking, this isn't necessarily the most natural choice. Which would have been f prime of x times g prime of x. But let's do an example that will hopefully convince you, hey, it should be this and not this. So, let's let f of x equal x, nice simple function, and g of x equal 2x squared. Okay? Well, then the derivative of f of x times g of x, let's plug in our definitions for f of x and g of x. That's the derivative with respect to x of x times 2x squared, which is the derivative of, using our algebra rules, 2x cubed, and then by the scalar multiple rule, this is 2 times the derivative with respect to x of x cubed, which now by the power rule is equal to 2 times 3x squared, aka 6x squared. Okay, so we now know what the derivative should be, and we'll see which one of these two rules gives it to us. Well, f of x times g prime of x plus g of x times f prime of x is equal to, okay, f of x is x, g of x, derivative of 2x squared will be 4 times x, right? We have 2 times 2x, plus, okay, g of x is 2x squared, derivative of x is just 1. Using algebra, this gives us 4x squared plus 2x squared, which is, in fact, 6x squared. So we know that this formula works. But now let's see what happens if we try the other way around. If we tried f prime of x times g prime of x, that would give us 1 times 4x, as computed earlier, and therefore that would just be 4x. Right? Because 4x is very much not 6x squared. So, the actual rule is this, not f prime of x times g prime of x. But this is the product rule, and therefore allows us to deal with any products of two functions. Okay, let's do another couple of examples. let's let f of x equal 3x to the 7th minus 4 all times x plus 1. And we want to find f prime of x. Okay, so the natural division of f of x is into the product of this with this. And that's exactly what we'll use here. So, f prime of x is the derivative with respect to x of 3x to the 7th minus 4 times x plus 1, which, by the product rule, will give us, first times the derivative of the second. So 3x to the 7th minus 4 times the derivative with respect to x of x plus 1 plus the second times the derivative of the first. So x plus 1 times derivative with respect to x of 3x to the 7th minus 4. Alright? These are nice and simple derivatives to compute using the sum rule and the power rule. So, exercise, do those on your own. And we're left with 3x to the 7th minus 4 times 1. Right? Because derivative of x is 1, derivative of 1 is 0, and they sum. Plus x plus 1 times 3 times 7x to the 6th. And then that's going to go away. Cool. So we're just left with this, doing the algebra all out. That's 3x to the 7th minus 4 plus, 21 x to the 7th plus 21 x to the 6th. Adding all of that together yields 24 x to the 7th plus 21 x to the 6th minus 4. And that would be our final answer. How about that? So, again, taking derivatives is a nice and easy matter. Just apply the rules in the order that works out. Product, sum difference, and then just some algebra from there. Now, you might ask, can't I just multiply those things together and then take a derivative and have it all work out? Yes, you can. But what if you have more complicated functions that multiply together not quite as nicely as two polynomials? For example, let's let y equal x squared times the square root of x minus 2. And let's say we want to find dy dx. Okay, well we have a natural product here. We have x squared times square root of x minus 2. So we have a natural division there. We can compute the derivative of this, and we can compute the derivative of this by realizing this is x minus 2 to the 1/2 power. So let's do that as x squared times x minus 2 to the 1/2 power. Oh, you know what? We can't actually compute that yet. We haven't talked about the chain rule. Slight change of plans. That would have been a good example too. Oh, slight change of plans. We'll talk about the x squared times the square root of x minus 2. So now the square root's only over the x, not over the 2. So this is x squared times x to the 1/2 minus 2. Well, what a shame, but here we go. Okay, to calculate this derivative, we first apply the product rule. And we see, okay, it's going to be the first times the derivative of the second plus the second times the derivative of the first. Alright, let's start computing. This is x squared times 1/2 x to the negative 1/2. Technically minus 0, right, from that minus 2. So we can ignore it and not write it out. And this goes to that by the power rule. Okay, we have that plus x to the 1/2 minus 2 times 2x to the first by just direct application of the power rule of x squared. Putting some algebra all together, laws of exponents say that this is going to be 1/2 times x to the 2 plus negative 1/2, which is 2 minus 1/2, which is 3 divided by 2. So we have 1/2 times x to the 3/2 plus 2x to the 3/2 minus 4x. And that's just using the distributive property there. Combining like terms gives us 5/2 x to the 3/2 minus 4x. So yes, this one also could have been done by multiplying beforehand and then taking the derivative. But I promise, with more complicated functions like the example I was going to do, if not for the fact that we haven't learned the chain rule yet. That's next video. Yeah, those are ones where you couldn't really do without the product rule. So, still a useful rule. Especially if you're working with things that can't even multiply together in a natural way, like say, an exponential function and a trig function, something like that. Let's do one more example with the product rule. Let's let g of x equal 12x times 1 minus 4 over x. And we want to find g prime of x. Okay? We have a natural product, 12x and 1 minus 4 over x. Let's use that to our advantage. G prime of x is equal to the derivative with respect to x of 12x times 1 minus 4 over x, by definition, which is applying the product rule. First, times the derivative of the second, plus the second times the derivative of the first. That's 12x for those of you who can't read my handwriting that small. Don't worry, I'm not offended by that. Okay. Let's do some calculus. This is 12x times, I'll write this one fully out, derivative with respect to x of 1 minus derivative with respect to x of 4 divided by x plus 1 minus 4 over x times derivative with respect to x of 12x. Okay, and that was using the sum rule to split up that. Oh, conveniently, already a little equal sign there for me. This is 12x times derivative with respect to x of 1 minus 4 times the derivative with respect to x of x to the negative first, right? 4 over x is 4 times x to the negative first, so by the scalar multiple rule, we can pull out the 4. That's a plus sign there. Plus 1 minus 4 over x times 12 times the derivative with respect to x of x. And again, that is by the scalar multiple rule. 12 can just get pulled out. Okay, let's start evaluating some derivatives. This is 12x times 0, right? Derivative of any constant is 0. Minus, applying the power rule to x to the negative first, gives us 4 times negative x to the negative second, plus 1 minus 4 over x just times 12. Derivative with respect to x of x is just 1. Now it's just algebra. This gives us 12x times positive 4x to the negative second plus 12 minus 48 x to the negative first. Let's write that as. Again, just using the distributive property everywhere. This will give us 48x to the negative first as well. And would you look at that? The 48x to the negative first are going to cancel out with each other because we have plus 48x to the negative first minus 48x to the negative first. I'll write it out. Plus 12 minus 48x to the negative first. And that's just equal to 12. I love that. Complicated looking function, but the derivative is just 12 after all. Alright, so that's how derivatives play with multiplication. Let's talk about how they play with division. For that, I'm going to need another piece of chalk. Sad life of a math teacher. This chalk is so expensive too. Or rather, I should say the sad life of a clumsy math teacher. You'd think being a rock climber would make me more, I don't know, on balance, but you would think wrong. Okay, let's talk about the quotient rule. Okay, let f and x be, or f and g be differentiable functions, yada yada yada. The derivative with respect to x of f of x divided by g of x is equal to g of x times f prime of x minus f of x times g prime of x divided by g of x squared. And this is as long as g of x is not equal to 0. right? If g of x was equal to 0, this would give us a divide by 0 error, and that function doesn't even exist, much less the derivative of it. So yeah, the quotient rule is probably one of the hardest ones students have time remembering. That's not how that saying goes. This is probably one of the ones that students have the hardest time remembering. So I highly recommend look at this, stare at it, repeat it to yourself until the sun goes down. It is derivative of a quotient, f of x over g of x, bottom times derivative of the top, minus top times the derivative of the bottom, all over the bottom squared. I'll say that one more time. Top times derivative of the bottom, minus, I said it wrong myself. Bottom times derivative of the top, minus top times derivative of the bottom over the bottom squared. So, if I'm even messing it up as I'm telling it to you guys, you can understand why so many students mess up. So, remember that formula, look at it hard, and let's do a few examples to kind of get some intuition for it. Again, I know it's not the natural choice, them's the breaks, for the exact same reason as the product rule doesn't work, actually. So for example, let's let f of x equal x to the fourth and g of x equal x squared. And we'll see why the rule has to be this precisely. Alright, well, the derivative with respect to x of f of x divided by g of x, that's the derivative with respect to x to the fourth over x squared, which is derivative with respect to x of just x squared by standard algebra. Okay? And that's just 2x by the power rule. So we know what the derivative should be, and let's see that this formula actually matches up with it. I'm pretty sure your book also has a proof of the product and quotient rules, so take a gander at that if you want. But I don't think the proof is particularly illuminating, so I'm not going to do it myself. Okay, using this formula now. This would say the derivative with respect to x of x to the fourth over x squared is bottom times derivative of the top. So x squared times the derivative with respect to x of x to the fourth minus top times the derivative of the bottom. So x to the fourth times derivative with respect to x of x squared, all divided by the bottom squared. So x squared squared. Okay, let's start computing these things and seeing that it matches up. This gives us x squared times 4x cubed minus x to the fourth times 2x, all divided by x to the fourth, which is 4x to the fifth minus 2x to the fifth, all over x to the fourth. That's 2x to the fifth over x to the fourth, which is 2x. Exactly as we wanted. So, this is the proper formula for the quotient rule. I understand that's hard to remember, but it is necessary for you to remember it. Alright, let's do another couple of examples. I'll even leave the quotient rule up for this one. Just because it's hard enough to remember as it is for me, without all y'all scrambling back and forth in your notes. Alright. Let's let g of x equal 12x divided by the square root of x minus 4. And let's say we wanted to find g prime of x. So this kind of situation is a natural application of the quotient rule. One function divided by another. So g prime of x is going to equal to, bottom times the derivative of the top, square root of x minus 4 times the derivative with respect to x of 12x minus top times the derivative of the bottom just going to put a little arrow there since I have ran out of space, all divided by the bottom squared. Alright, let's start simplifying. This is the square root of x minus 4 times 12 minus 12x times, let's leave that one in derivative form for a second. This is x minus 4 to the 1/2 power. Yes, that's again a chain rule problem. Darn it. All divided by just plain x minus 4. Square of a square root is the original thing. Okay, don't worry about this one for a second. I'm going to tell you what that derivative is, and for the y, we'll see it in the next video. But this will give us 12 times the square root of x minus 4 minus 12x times 1/2 x minus 4, all divided by x minus 4. Alright, and now if we started simplifying, this would give us 12 divided by the square root of x minus 4 minus 6x. That x minus 4 and that x minus 4 cancel out. 12x times 1/2 is just 6x. And then 12 times square root of x minus 4, this is 12 times x minus 4 to the 1/2 divided by a full power of x minus 4, and it leaves square root on the bottom. Alright, don't worry too much about that example. Again, going from here to here requires something called the chain rule, which it's such a common rule and such a useful one that apparently I'm making examples that require it without even intending to. So that's on me. Let's make up for it by doing a couple more examples that will not involve the chain rule. Maybe a very similar one. Let f of x equal x minus 1 divided by the square root of x plus 1. Okay, so this will be a bit better. F prime of x is bottom times derivative of the top. So square root of x plus 1 times derivative of this top is just going to be 1. Minus the top times the derivative of the bottom in case that wasn't clear. I realize I should have probably written that out. Times derivative with respect to x and square root of x plus 1, all divided by the bottom squared. Okay, what's this equal to? Well, this is the square root of x plus 1, just from that first part, minus x minus 1 times, this is x to the 1/2 power, and this is a constant, so that gets zeroed out by the derivative, and we're left with 1/2 x to the negative 1/2 divided by square root of x plus 1 all squared. Let's do some algebra. This gives us the square root of x plus 1 minus 1/2 square root of x plus 1/2 times 1 over the square root of x. All divided by the square root of x plus 1 squared. And now let's start simplifying. And this is equal to 1/2 times the square root of x. We have a 1 square root of x minus 1/2 square root of x, so we're left with just 1/2 square root of x plus 1 plus 1 divided by 2 times the square root of x. All divided by the square root of x plus 1 all squared. I don't think we're done here. You could say, oh, good enough for me. I like to go the full step on simplification and say this is 1/2 times the square root of x plus 1 plus 1 divided by the 2 square root of x all times the square root of x over the square root of x, in order to make these things all common denominator. We can do that, or in fact, let's do them one by one to make it more clear what's going on. This will be 1/2 square root of x, so the square root of x divided by 2 times square root of x over the square root of x plus 1 times 2 square root of x over 2 square root of x plus 1 over 2 square root of x, all over the square root of x plus 1. Okay, so why did we do that? We did that to make sure that all of our things on top would have a common denominator, so we can put them together and start using fraction rules. This gives us x over 2 square root of x plus 2 square root of x over 2 square root of x plus 1 over 2 square root of x, all divided by the square root of x plus 1 squared, which is, finally, using all fraction rules at once, you get x plus 2 square root of x plus 1 divided by 2 times the square root of x times the square root of x plus 1 squared. Now, the keen observer among you might notice, hey, crap. Yeah, let's erase it. Y'all can always go back in the video. Alright. Keen algebra observers among you might notice that this is in fact equal to the square root of x plus 1 squared divided by 2 square root of x times the square root of x plus 1 squared. Those cancel out and we are left with 1 divided by the 2 square root of x. So, bit of a long road to Rome right there, but we can do it by just carefully applying our rules and then carefully applying our algebra. That's all there really is to taking derivatives. Apply your rules, apply your rules, apply your rules, and then a bunch of messy algebra to simplify to something that looks pretty nice. Let's do another example. Yeah, I want this whole one off my board. It was frustrating. So, one more example. Let's let f of x equal x cubed minus 2 divided by x cubed plus 2. And let's find f prime of x. And I'll do this one step by step. F prime of x is equal to, by the quotient rule, bottom times derivative at the top, minus top, the walls are coming down, minus the top times derivative of the bottom, all divided by the bottom squared. Alright, so that's just the quotient rule getting applied directly. Now let's start working with these derivatives here. This is equal to x cubed plus 2 times derivative with respect to x of x cubed minus derivative with respect to x of 2. This is by the sum rule. Minus, again by the sum rule, x cubed minus 2 times derivative with respect to x of x cubed plus derivative with respect to x of 2. All divided by x cubed plus 2 squared. Which equals x cubed plus 2. Okay, here, power rule, that goes to 0. So we're just left with 3x squared. Here, we have minus x cubed minus 2 times, again, 3x squared. All divided by x cubed plus 2 squared. And we can do some algebra to simplify from there. We're going to have 3x to the 5th, that would be, minus 3x to the 5th, so those are going to cancel, plus 6x to the 4th minus 6x squared. Sorry, plus 6x squared minus 6x squared. So, let me write that out before I confuse myself any further. We have 3x to the 5th plus 6x squared minus 3x to the 5th plus 6x squared. The minus signs, right? Minus and negative is positive. All divided by x cubed plus 2 squared. This is equal to, okay, 3x to the 5th are going to cancel out, plus plus, and we're left with 12x squared divided by x cubed plus 2 squared. Alright, so that one wasn't so bad. Even moving step by step. Algebra at the end was a little hairy. That's mostly because I was trying to do it in my head and being stubborn. Don't be stubborn. Don't be like me. Write out your steps. It'll save you a lot of trouble in the end. I'm just not particularly known for saving myself from trouble. Alright. Derivative of x cubed minus 2 over x cubed plus 2 is just 12x squared over x cubed plus 2 all squared. Follows pretty much immediately from the quotient. Alright, I think that's enough examples for now. We'll be able to do more in class together, obviously. And yeah, in the next video, we'll talk about the chain rule, which I have mentioned several times in the course of this video because it's just so useful. And after that, we'll basically be at full power with regards to taking derivatives. See you guys there.